Okay, I think everybody's back in here and everybody's had a chance to grab coffee and my microphone is still on. Okay, so we are going to now start our introduction to scanning electron microscopy. This is my version of a class type setup, including theory and operation. So we're not going to go through the exact logistics, but you'll see where a lot of the settings that Serena is going to give actual hands-on instruction later today come from on our SEM, as well as you should get a good background in what a lot of the terminology means so that you can be a little fluent in that, and what the different types of SEMs are. Sometimes a little bit of what we have and what others have and we don't, depending on the design. Okay. Why would you want to use an electron microscope at all? Well, why would you want to use a microscope at all? A microscope, invisible or whatever other type of light, magnifies things beyond what the human eye can see. An electron microscope has the ability to magnify things significantly beyond what a light microscope can do. And everyone sees slide, by the way. If you need to move up, please feel free to do so. All clear? Good. Okay. Okay, so if you want to be able to see something like a viral particle or a cell or individual atom positions, light microscopy can't get you there. Electron microscopy can. Electron microscopy goes all the way back in concept to the late 1920s. Just as people were beginning to understand what electrons were, a researcher, in fact, a pair of researchers in Germany published designs for an electromagnetic lens, which would be capable of focusing electrons much more precisely than visible light could be focused. A researcher engineer named Ernst Ruska, using that design, built a working prototype of a transmission electron microscope in the 1930s. They initially were able to amplify or magnify a metallic grid by a factor of 17. By 1933, they had a design that could magnify up to 12,000 times. So pretty quick and efficient there. They partnered with the company Siemens, a German industrial company, to develop the design in 1937. You can imagine what the links I came across by searching for German industry in 1937 produced. So this literally fell right in the middle of that. The work and several of these folks, including Ernst Ruska, were awarded the Nobel Prize in 1986 for their design of the first electron microscope. The next steps were kind of delayed for 10 years, a bit of an incident. The electron microprobe, which is very closely related in design to a scanning electron microscope, was designed in a PhD thesis in the early 1950s. And the last innovation really required to make these things available was an electron detector. We'll talk about how that design works at some point. That electron detector for detecting the shape and type of electrons bouncing off stuff became available in about 1960. That allowed the development of the first full scanning electron microscope by Cambridge Instruments in 1964. There's a few other innovations that had to be done there. It wasn't just the electron detector. For a transmission electron microscope, you're just bombarding your sample with electrons. So you don't need to control it as much because your sample does a lot of the control for you. For a scanning electron microscope, you have to actually be able to scan across a surface. You need a very finely controlled electron beam. So how you control the electron beam is another innovation that came in the early 1960s. They thought originally that there was going to be more demand for the microprobe, and by 1968, there was 150 microprobes and over 500 scanning electron microscopes because of how flexible this type of instrument is and how many different things you can use it on for imaging purposes. The advantages of the SEM, we mentioned one of them already, is resolving power, magnification. You can zoom in on things to a degree better than you can with an optical microscope. Here is a 100 micrometer scale bar. This is almost at the limit of what you can image with an optical microscope. You can get a little smaller than this, but note the resolution. You can distinguish micrometer and sub-micrometer scale features with high accuracy. Furthermore, note this difference between these two images. In this one, with the settings correct, there is some z-axis. You can see three-dimensional topography. You can see the shapes of materials at the same time as you're getting high magnification. So you're not just limited to a flat surface. You can see things that have structure to them. And with some work, you can also get compositional information at the same time as you're doing imaging. These are all powerful benefits of electron microscopy. Roughly speaking, we can think of SEMs as broken down into two categories. One of them is the type, this is the Wikipedia image of the type you'll be using today. Over the last 10-ish years, maybe 15 years, there has been a proliferation of fairly low cost, fairly simple desktop type SEMs that make electron microscopy much more accessible to labs that have previously not had them. On the other hand, we have the lab scale version. With a slightly different design, this one would have as many bells and whistles as you can fit onto it, including lots of different types of detectors that can do many different things. We'll see how much time we have to talk about all those. Serena, did you want to add anything on this slide? Okay, this is one that she wanted me to have on there. Okay, advantages of each type. The highest quality images you could get on a three-dimensional or non-transparent surfaces, it's going to be on a floor model or FE-SEM. We will talk briefly about what that is in a few minutes. That's where you're going to get the best resolution. You can also specialize those. There are lots and lots of ways you can design an SEM to do a specific type of observation that your lab might need to do. Different types of materials can be tuned certain ways. It is also possible in one of those floor models to fit a fairly large sample in there. You can fit a full rock in some cases into a floor model SEM, or I've put a platinum crucible for experiments in those before, and you close the door and you move the stage and you're good. And so large three-dimensional samples can be put in there. You can also, in that type of SEM, set it up to watch things as they're happening. If you want to observe chemistry happening, if you want to observe biology doing something, if it's stable in the SEM environment, you can actually watch chemical reactions. You can watch things change in your sample if that's the thing that's interest to you. The desktop or tabletop SEM varieties are much cheaper. This makes them far more accessible than the full lab scale facilities. You can have multiple ones of these on a single university and give everybody access to them. Sample preparation is often easier. You don't have to worry as much about everything holding together in there. The startup and setup are quick. Training required can be quite limited. We can put an undergrad on ours in a few minutes if we need to. Compact design means you can put these everywhere. You don't need specified power requirements in most spots. You may not, or you may or may not even require a lab manager or operator. Someone trains someone, and then you don't need a full-time lab person, cutting the cost there as well. The LPI SEM facility is one of these desktop SEMs. It was purchased with an investment grant from the University Space Research Association, which is kind of the headquarters that runs the LPI. That's kind of one of our bosses. It became a planetary science enabling facility in 2022. We have a number of different modes that we're going to go through. SCI, BEI, and EDS. Those don't have to mean anything to you right now if you're not the SEM lab manager. They will in the next 2 hours. We also have variable pressure or environmental mode that will be important for a few of you to play with. We also have an evaporative carbon coater. Thank you to Aaron Burton for that. That was funded by the Planetary Science Enabling Facility grant. There is no cost to use this facility, and roughly 50% of its time is available for visiting scientists outside of the people directly in the LPI. So if you want SEM time, we have it, and we want you to tell others that we have it. Please tell others that we have it. If you have others at the lab at Rio Grande Valley or whoever else, UT Dallas, please tell others we have this sitting here if they need it. Now, start going into the details. I want to build or run a scanning electron microscope. What does that mean? What do I need to make this work? This is the structure of a scanning electron microscope. I've triple checked this. Everything that I use as an image should be cited at the bottom if you need to go back to the reference. Okay? So everything should have a citation, either a paper, an industry source, or Wikipedia when available for Creative Commons licensed images. The structure of an SEM starts with an electron gun. We start off at the top generating free electrons. We send those electrons down a column past a series of lenses and apertures until they hit our sample. When they hit our sample, there are a set of interactions that take place between solid matter and an electron beam that set off responses that can be detected by the right type of detector. We're going to go through pretty much all in some amount of each of these types of pieces of equipment. Give you a little calibration on how everything here works. This is not going to teach you how to service an electron lens. For a lab manager, that's beyond this course, but you're at least going to know what they are. Let's start at the top. Electron guns. How do you generate a stream of electrons? There are 3 basic classes of electron guns. Tungsten filaments, some other types of crystal filaments, and a field emission source. So when I said I'll get the abbreviation FE in a second, that is a field emission source. Let's go into each of those a little bit. Perhaps the most common, I don't know if this is still true, but this was true at least 15 years ago, and I think most electron microprobes still use these. You go back and find a 1970s vintage microprobe, they're going to use this, or an electron microscope. They all started with this. This is a tungsten filament. It is a coiled piece of tungsten wire. You apply a voltage across this piece of wire. Because the wire is bent, there's some resistance to it. That causes heating. The heating of that wire, it's like a light bulb. It starts to glow. In this case, it's glowing by releasing a cloud of electrons. So this wire generates free and loose electrons. Now we apply an accelerating voltage to draw the electrons away from this tip, and we have a beam of electrons heading towards the column. That's the basic operation of one of these. There are still some benefits to these. This is this one is a page where you can buy tungsten filaments for your electron microscopes. There's lots of little shapes of them. They are cheap comparatively. They are easy to replace, and compared to a field emission gun, they do not require as high of a state of vacuum. So the maintenance is a little less in terms of that. The type you will be using for the next 3 days is a lanthanum or cerium boron crystal. The LPI-SEM is one of these. Cerium, right? Okay. These are, in general, similar in operation to a tungsten filament, meaning that you run a current across it and it generates heating that generates an electron cloud. In this case, this type of filament can be up to 10 times the current or 10 times brighter than a standard tungsten filament. The electrons are also emitted from a narrower point. The tip of this is the spot where you have precision release of an electron beam, allowing better focusing and better resolution. The energy spread of the electrons is narrower, so you have a control to the energy that's coming off. The filament lifetime is quite a bit longer, does not burn out as much. Disadvantages, they're more expensive than a tungsten filament. A better vacuum is required to make this work. And again, with this one, to get it so that the beam is operating correctly, saturation of the beam can be time consuming. The fancy ones. Anybody have a field emission gun that they've used? Field emission electron microscope? I have. Okay, in the back. We don't have one here, but some of you might. I've used these before. Okay, these are the fancy ones. To find these, you will find these mostly in your floor models, because making these work well requires operation of vacuum systems, operation of maintenance systems. So if you're going to spend the money on putting one of these things in, where you need the extra resources, this is the place where you put all the bells and whistles. The extra detectors are often on this design. For a field emission gun, rather than heating, you apply a voltage to this tungsten tip, and that causes draw off of electrons. So we're not heating it to do this. This is a cold emission here. There is a voltage applied between that tiny little tip and an accelerating plate. This leads to a dramatic amount of electrons coming off of this source. So strong enough voltage pulls electrons off the thing from that single point. All of the stuff that I said was getting better as you went to the crystalline sources. The field emission gun takes that to its extreme. It's the highest brightness. It's the most precise tip that you can get. It has a nice long lifespan. It is expensive and requires an ultra high vacuum, because if you have gas molecules running around, they will interact with this big electron cloud. Okay, so the difference between our SEM and a field emission SEM. These are the most precise. These will get you the best images down to the smallest features. These will take the most expense. They will be the hardest to use, hardest to maintain. They are big instruments to do this correctly. Pause for questions. Those are our 3 types of electron guns. All clear so far? This is the kind of stuff I'm going to drag you through for the next 30 minutes or 45 minutes or so, because I think it's useful to get the terms down, because when I first used a field emission electron microscope, I had no idea what I was saying when I called it a field emission electron microscope. Okay, our next step. We've got electrons from our electron gun. We now to get this down to our sample. The electrons are accelerated by some sort of accelerating voltage. That was in the gun. We pull them off with applying some sort of voltage to it. And then there's a set of lenses. And in an electron microscope, these are not lenses in the optical sense, so they're not glass. These are magnets that apply magnetic fields that cause electrons to spiral where they need to go. Now, a perfectly ground optical lens can be super precise. Go talk to some glass making folk. They're really good at their job. Okay. Electron lenses are very controllable. They are nice and flexible because they are electronic. This is the basic design of an electron lens. It's a coil that you run a current through. So if you need to adjust your lens, adjust the current at various spots, and that will allow you very precise control over the electron beam because we are moving electricity in a magnetic field. That goes all the way back to Maxwell and people in the 1800s. Move charges in a magnetic field and you have a strong control of that. So we're Michael Faraday's experiments and stuff like that. That's what we're doing here. Because this is super precise in terms of current, any little difference in this magnet can have an effect on the electron beam. You get a tiny little bit of contamination on one of these lenses, and it will affect how the beam interacts with the surrounding magnetic field. The lenses control how focused the current is, how the beam moves, and also the depth to which control happens. There is another important term on here, seen right here. This is the aperture. This is a common setting that you will be able to adjust on electron microscopes. The aperture is the opening in between the lenses that determines how wide of a beam comes through. Effectively, this is a current control. If you open a wider aperture, you can get more electrons coming through. A more narrow aperture will reduce the number of electrons coming through. So the lens has both of those effectively built into it. A magnet that controls the current and an aperture. Electron lenses have several known sources of error. I don't think we call these flaws. These are the things that you need to manage in an electron lens. By the fact that it's a magnet, electrons that are closer to the magnet will feel the magnet more than electrons in the middle. This is one of those magnetic forces that varies by the distance squared. So by rule, by physics, the outer portion of the beam is always going to be a little bit deflected in a weird way. This leads to a phenomenon known as spherical aberration. This is like a lens being misgrounded. When the Hubble Space Telescope was originally unable to focus, it could not focus because its lens was misground, leading to spherical aberration. This is a difficulty in bringing everything to a focus. It's impossible to fully eliminate it. This is one of those laws of physics that we can't get rid of to build this. There is always going to be a little bit of spherical aberration in an electron microscope image. I've seen this in terms of doing images and then stitching them together. There's always a little bit of bowing outwards at the edges. So if you want to get a large enough image, you often have to focus on the area where spherical aberration is minimized and then stitch around this to make it work. The other effect on here is astigmatism, which is, this is the complicated figure at the left. It's any effect that leads to a non-uniform pull of the lens. In astigmatism, we have a lens here. It's trying to focus right here, but something has caused it so that a portion of the beam is instead trying to focus here. So it's trying to focus at one spot, but because something has happened where it's not perfectly focusing, it draws a portion of the focus off. That is astigmatism. Now, if I go into and scratch one of my lenses with a knife, that's going to cause astigmatism, meaning it will not focus correctly because of that bit of damage. More commonly, in an electron microscope, what happens is, here's your lens position, a little bit of contamination over time, building up on these finely produced, well-manufactured lenses, will gradually start drawing off the focus. Well, this is either going to ruin our electron microscope, or we're going to have some way to correct this. There is some way to correct this. There are what's called stigmator coils. Stigmator coils are an extra set of magnets in the line where you can adjust the current through these magnets to account for any distortion that has shown up. Stigmation or astigmatism is thus an inability to focus fully, and you have extra magnets to help you correct that in basically every electron microscope. So if you're dealing with the astigmatism section or selection, here is a stigmatic image. Here is one where the magnets have been adjusted to allow that to be corrected. Stigmatism shows up most, and you can recognize it when you go slightly out of focus. Okay, so if I have my beam precisely focused on my sample, and I just can't get a good image, can't get as good of an image as I want, well, that might mean stigmatism has shown up, so that my beam is getting deflected and not coming to a full focus. Okay, how do I test this? I take the beam and move it slightly out of focus. If it's stigmatic, what will happen is it will go out of focus in one direction more than another. And then I go the other direction. So if I go up in focus, it goes this way. Turn 90 degrees. If I go down in focus, it stretches out this way. If your beam is well controlled, then as you go in and out of focus, things will just stretch out and come back to focus. But if they stretch out in a single direction, that is the sign of a stigmatic image. That means you need to apply an additional magnetic field to correct for this. That's the usual routine for this. Our electron microscope has an automated system to do this. Serena, I believe, will be showing you where that is on ours and maybe giving you a chance to play with this a little bit. This is always the one I struggle with. This is the hardest adjustment to train yourself for. This is one I can show it to you. This is one you got to practice. Okay, so now we've set up this big wordy chart. Okay, we've gone through the lenses, we've gone through the current, we've gone through the beam. Getting an image, and a high quality one, will be a function of our settings. Different types of settings produce different responses. So, tungsten filament, the smallest possible spot I can get with a tungsten filament is 10 nanometers. A field emission gun can give you a spot that is an order of magnitude smaller. From what I found, the best reported beam resolution of a field emission gun on a Hitachi was just over 1 nanometer. Now, you don't always do that, but you do, okay? So that's the limit for what you can image with a SEM. As you adjust your settings, the beam responds to this. If I increase my probe current by bringing more electrons through, the beam becomes larger. Well, a larger beam limits the exact focus that I can get with my SEM. But a higher current and larger beam will allow me to brighten things up so I can see more features with the larger beam and improve the image quality. Current and voltage are different settings. Current is in part controlled by the aperture. Voltage is the accelerating voltage that sends the electrons down. Low voltage operation can lead to the beam spreading out. But at a low accelerating voltage, the beam has less penetrating power. So it goes less into the sample. If I'm trying to image just the surface, voltage can be a factor in how deep my observation goes into the sample. The other thing we mentioned was the depth of field. Well, we have the ability to focus on a range of depths. If I want to manage depth of field, a low current, small aperture, and position my spot sample far away from the beam source will let me see something with a greater depth to it. So I can see around edges or see different features. On the other hand, if I bring my sample up, I get a better focus. The beam is much more tightly controlled, closer to the lenses. These are some of the operating trade-offs that come just out of the design of the SEM. Control the current, control the voltage, control the lenses. That can give you different beam sizes, different penetration depths, different types of interactions with the sample. Specific types of imaging, EDS mapping, backscattered electron mapping, will then pop out of this and be influenced by these settings. Pause for questions here. Everybody with me so far? Okay. Now, every SEM, literally everyone has some version of a vacuum on it. Almost everyone has more than one vacuum on it, in fact. The fanciest ones are basically the jet engines. A turbo pump on most SEMs literally spins like a jet engine to accelerate air in there. The electron beams themselves often have an extra fancy gun or extra fancy vacuum that ionizes things and then pulls ions out of the way, because that needs to be held at a high vacuum, particularly on the field emission guns. Every SEM will thus have a boundary between where your sample goes in to hold it, get put into the vacuum, and where the sample comes out. Sample exchange is thus something everything is going to have to do.
Do you keep the vacuum on all the time if you're not using the SEM?
Yes, okay. Unless it's down for service, keep it under, or the power's out. Keep it under vacuum unless there's some reason not to. Now, what under vacuum means can have more than one meaning depending on the SEM. But pretty much every SEM should just use, especially the electron gun, you don't want to let material get in there because that can do chemistry with the electron gun. So atmosphere will interact with tungsten. But yes, effectively, the SEM always stays under some amount of vacuum, which you can then control. The sample exchange chamber. There are some designs, very common ones, where if this is not done properly, then it can do damage to the SEM. For example, this specific type of SEM, if you don't load your sample in here properly, your sample can fall off into the electron, into the machine, and you wind up having to literally open up the SEM and take it out of vacuum to get your sample out that you dropped in. This is less than ideal. I have not done that error, thankfully, okay? But I know of people who have. So if you're in a lab, pay attention to what they say in terms of sample exchange. This is one of the places where you can actually mess things up. Our desktop SEM is built where this is basically not a problem. Ours is almost idiot-proof, no offense, okay? Literally, as long as it fits in there, it is difficult to mess ours up. That is one of the benefits of a desktop SEM. And when we say you can train a person to use some of these very quickly, this is one of those spots where if you can simplify this down and make it easy, then you remove a failure point. You may lose a little bit in terms of flexibility, but this is one of the benefits of a desktop design. Remove this failure point because this is challenging and sometimes requires precise manipulation of a system. Now, we have loaded our sample, we have put it under vacuum. We are going to hit our sample with electrons. What happens when we hammer our sample with electrons? We hit our sample. The interaction between the beam and the sample is complicated. Electrons do not only interact with the surface. Even at low voltage, there is an activation volume that is generated. The beam comes in, strikes the sample, and electrons go some distance into the sample. While it is doing that, it produces a variety of responses. This gives the SEM some of its power because you get multiple responses from a single electron beam. And each measurement will say something about the sample. We will not focus on all of these this morning, but we will focus particularly on the ones that our SEM can do, which are going to be secondary electrons, backscattered electrons, and characteristic X-rays. Those are going to be the three that we'll focus on here because our SEM does that. If we have time to talk about the other ones, I can talk about the other ones later. Okay? What are these three responses? Backscattered electrons are electrons that bounce back. An electron comes into a charged field. It feels the charge of that field that it's moving into and swings around it. That is the path of a backscattered electron. The electron from the gun comes into the solid, feels the nucleus of something, and swings around the nucleus to fly back out. This happens due to the charge on a nucleus, and thus the response is proportional to the charge on the nucleus squared. So backscattered electron signals are going to respond to the average atomic number of the material under electron bombardment. Electrons come in, feel the nucleus, and swing around being fired back out. The heavier and the more charged in the nucleus, the more it swings around and comes back out. Here is a backscattered electron image that I took of a Martian sample at one point. I like this one because I used this. This dark grain right here is an iron-rich olivine. Around it is plagioclase. You should not be able to see that right here because I have changed the settings on this beam to focus specifically on this grain. In this grain, I have an iron oxide and an iron sulfide. By adjusting the settings, I can see the difference between one material and another. And the difference in brightness between this grain and this grain. They're telling me a difference in atomic number. In this case, there's probably more iron in this one, but also sulfur has a higher atomic number than oxygen. So the combination of iron and sulfur is giving me the strongest signal in backscattered electrons. And I can tell this sample from this material from this material, I am directly probing what the material is made of and its average atomic number. Worth knowing on backscatter. is that there is a strong dependence in backscattered emission with the angle of a surface. If a surface is flat and you fire an electron beam at your flat surface, your strongest response is back in the direction of the beam. We'll get a strong signal on a flat surface shot back at you. If you have a surface that is rough, as you go away from horizontal, the strongest flux of your backscatter will tilt horizontal. In this type of detection, thus, there is some benefit to a flat surface, because a flat surface aiming back at the vertical will be giving you the strongest signal in your detector. Whereas a rough surface, you will lose observation around the edge. Wrong direction. Okay. The other type of detector that we're going to talk about in RSEM is a secondary electron detector. Okay, so we talked about backscattered electrons. That's an electron comes in and zooms around a sample. For a secondary electron, a primary electron comes in and instead of zooming around the nucleus, hits the outer shell of electrons around an atom and knocks an electron loose. So the primary electron is the electron that comes in. The secondary electron gets energy from the electron coming in and gets launched off of it. These electrons bounce in every direction once they're emitted, including into the solid. Some of them will intersect the material surface and escape, and those can be detected. There is a big difference in the energy of the electron between a backscattered electron and a secondary electron. That is how you tell them apart. That's why they behave differently. And that's why you're going to need a different type of detector for each of them, because the energy is going to be dramatically different. When you have a rough sample in secondary electrons, we see a different effect from backscatter. In secondary electron generation, the electrons head out in all directions. Okay? If they're heading into the sample, then they head out in whatever direction is shortest. If your sample is fully flat here, electrons come in, get generated, and then escape from some depth. If your sample has a rough edge in this type, well, here we send an electron into the sample. It's generated here, has a longer path to get out here than it does here. In this case, unlike the backscattered case, the short direction will have a higher electron flux. Secondary electrons, thus, are often good at analyzing differences in sample shape. If you really want to get a high quality image of a rough surface or a powder, secondary electrons are the way that you're going to see the rough edges. Whereas backscatter is your compositional contrast. Now, they can interact with each other and do both. But if I want to see the edges and shapes of a very fine-grained material, secondary electrons are how I might do this. Let's take a look at a secondary electron image. This is something from NASA. This is a little crystal in a VUG in an Apollo 15 lunar sample. Okay? Take a look at this crystal right here. Which part is the brightest, the edge or the center? Answer. The edge. Why is the edge bright here? Because we're looking at secondary electrons. If they go into this part, they have a long path length to get out. If they go in right here, they're escaping along the edge, leading to a higher signal around the edge. So small projections, small little bits on the sample surface tend to be brighter than the sample itself because that has the reduced path length. So more of the secondary electrons are able to escape along those edges. Okay. Which of these is which type of image? Okay. One of these is just showing surface topography. One of these is showing composition. This one was taken from Wikipedia. Okay. It's kind of a flat surface here, but here we're seeing grains and grain boundaries. Here we're just seeing little perturbations on the surface. This, in this case, is a backscattered image. This is the secondary electron image, okay? Serena provided me these, so I'm gonna now turn this one over to you folks. This is your image, so don't waste this, okay?
I think mainly an example, well, it's an example of two things. One of which I just said, you got on the left, you have backscattered image, you've got a big black thing there, and you don't know what it is, graphite or silica or something of low atomic number. When you look in secondary electrons on the right, you see it's a bit, holes in it. So you can ignore it. It also shows that in the backscattered image, you see phase contrast between, say, this area and this area, which are in fact different minerals. Whereas in secondary electrons, you can barely see that if you're not getting the composition.
What would be the hints? Okay, we have a rough surface, right? For a secondary electron image, we should be seeing zones around the edges of grains that are coming out bright, because that's the escape path. So which one of these is the secondary image, the left or the right? The one on the right is the secondary electron image. The one on the left is telling us there's some structure here. There's not a big compositional difference. Okay, couple of spots to point out here. I wanted to add this in, okay? If you have one of these big regular electron microscopes that you open and can look into, oftentimes the secondary electron detector is off to the side because secondary electrons head off in every direction. Backscattered electrons head straight back from polished sample. Backscattered electrons have much higher energy than secondary electrons. So secondary electrons will often be detected off to the side, whereas backscatter detectors are right in the path of the electron beam. Here's a backscatter detector right here. We have a hole in it to let the beam come through, but then it basically surrounds the beam. And if you're doing backscatter collection, you might even be able to insert and remove this in some microscopes. I've had to do that before, where to get a good backscatter image, you have to put the backscatter detector in so that it's in the path of the reflected electrons. The different designs capture different bits of the energy spectrum. So this one collects these low energy electrons that are bouncing around the whole thing. This is a big, broad semiconductor detector that gets all the high energy stuff so that you're not necessarily amplifying the voltage. With me so far? I don't want to spend too much time on those on this version. We can go into depth more on that later if we have time. Depth of field was one of those other things we referred to here. This is my depth of field slide. In an electron microscope, there is a specific plane where things are perfectly in focus, and then there's a range around it where the focus is good enough. You saw this on some of those rough surface images just a second ago, where there's not a single plane that's in focus. You can see the whole sample. This can be up to several millimeters if you need it to be. So, a truly moderately rough sample can be imaged in SEM. This allows for the 3D quality of many SEM images. For the best quality image on a single surface, position close to the sample is ideal. So raise your sample up for high quality images. We call this a short working distance. The working distance variable is how far down the thing is. For images of a surface with topography, a larger working distance will allow for a greater depth of field, meaning you can focus on a larger and broader range of things. Smaller aperture sizes also lead to larger depths of field. So if we squeeze this in with a small aperture, so a small controlled beam, that leads to a larger depth of field. If we spread out these green lines, that focuses onto a finer depth of field, or a finer point. Got that? Everybody following how the settings are kind of interacting with one another as we go through this? Okay, so now a little bit of talk about how to get good quality images on different things. Okay, if we're trying to get a high quality backscattered electron image, our goal with this type of image is to recognize different types of materials. So what we want is a high flux of electrons coming back so that we get a strong signal, giving us a map of the high mass atoms. We can then adjust the settings to be able to distinguish between similar phases. So note the way that Serena has this set right now. We have a pyroxene and a plagioclase here. You almost can't tell these apart because for now, she has the setting here where we can see the iron-rich oxides and not other things. The secondary electron detector, on the other hand, is usually used for things that have some amount of surface features to them, some amount of topography. You can see minerals or organic compounds, dust. Okay. There is some influence of backscattered electrons on secondary electron detectors. The detectors are detecting electrons with certain images or certain energy ranges, but there's some bleed over. The high energy things cause scattering around the sample, and you get distinct signals here. Secondary electron detectors are put out of the way so they have a view in from the side with computers that process the image to give you kind of a shape to it. Let me skip that. To do a high quality backscattered electron image, what you need to do, first, focus the image. Bring the image to the spot where you're happy with the focus. You can see the features you want. And then you will need to set brightness and contrast. Brightness will be influencing how much of a signal you get off of there. Contrast will determine whether you can tell one thing being different from another. Do I want to image the entire periodic table so that I'm seeing all of my phases, but things that are similar atomic number have similar contrast? Or do I want to focus in on a specific range of materials? In this setting here, you can tell the distinction between a rare earth element grain and a zirconium grain. My potassium feldspar and whatever the ground mass is nice and dark. This is a certain set of contrasts. Contrast on the SEM is what am I looking at? If I look across a low contrast, broad field, things that are similar in atomic number will blend together. But if I instead pick a specific range of contrast, I can bring out a feature. If I do that, then everything that is high mass might be indistinguishable. So on this one, if I narrow down to be able to see my feldspars, then the pyrite and the monazite and the zircon, all these high mass things, will all just wash out and just be indistinguishable. So contrast is going to be what's going to allow me to select which range of materials I want to see and focus on in my image. This slide is kind of an overview. This slide and the next one is kind of an overview of when you put something into RSEM, what do you need to do to get RSEM to respond? Many will have different versions of this. So a field emission SEM with a big working distance, you may have a setting here where ours is set working distance right here. A different facility might say set working distance right here. Or switch detectors, insert the detector you need. Those things can be different on a different SEM. This is the outline for ours because we're working on ours. First thing you do after prepping your sample to load your sample is prep it. We'll talk about that later this afternoon. And add your sample in and set the working distance, which means you have to decide for ours, what do we want to do? Are we doing high quality image of a single spot? Are we doing compositional mapping? Are we doing a big three-dimensional sample where we need a big working distance? That's something you have to decide early. Settings that you can control. The vacuum level, we'll talk about that in 1 second. The accelerating voltage, we've talked about this. This is the energy that drives the beam down. The current, meaning our aperture controls that in this, as well as how much energy is pumped into this. What type of imaging do we want to do? And also, how long do we collect image data at any single point? Do we collect a high pixel image where we move across, or do we collect a more broad image? Those are things we can select and change. We then move to the spot we want to go to on our sample. Once we've set all these settings, we zoom in to the level we want. We adjust the focus so that we are now focused on our image, fixing any stigmatism if needed. Hopefully it's not today, although you get to play with that. And then you adjust your brightness and contrast to bring the feature of interest into the field of view that you want. You then select, well, do we want output as a TIFF file or a JPEG file or something else? So image compression is a detail on there. You can also often select on an SEM, do I want the full frame or do I want a data bar at the bottom? If I'm stitching together 80 images on a single slide, I don't want a data bar at the bottom because that will block my ability to stitch things together. We haven't talked about much on compositional mapping yet. We will have a slide on that in a second, and I have content for that this afternoon. We'll talk more about that later. And then the final step for Wednesday from Serena's section again is going to be combining multiple types of images and then turning that into classification details, maps of various phases, and so on. Okay? These are little bits of windows and previews into stuff we'll be doing this afternoon. So this afternoon, we have a whole session on sample preparation and EDS. Here I get one slide on each. Sample preparation is going to matter for limiting noise. One of our biggest challenges in the electron microscope is electrons. In other words, charge. If I am firing an electron beam at a material, that beam will become, or that material will become charged. This is a problem because a charged material will start sending out its own energy. This will lead to brightness across my field that is non-constant because as charge increases in one zone or another, it will start changing the response of the electrons. Lines going across your screen are a very common result of charging on your sample. Another fun one is image distortion, because as your sample surface builds up a charge, the electron beam It's deflected by this charge that's building up on the sample, meaning that your sample will seem like it's moving because the electron beam itself is moving and that's changing the signal. We may not be able to get a stable stereoscopic image, so we might not be able to see the three-dimensional surfaces either. Carbon or gold or other metal coating is one of our tools to get around this. If our sample is nice and conductive, we don't have to worry about this. If we have a non-conductive sample, I couldn't resist using this one. Here is a non-conductive bug that has been coated with metal to make it conductive. A thin coating of metal will make a surface nice and conductive and limit or prevent charging so that any electrons that are spare get moved away back into the sample. If you make this nice electrical connection between your sample holder and your sample, charge can get removed. It's never perfect. You have to maintain things sometimes. If you're at a high enough current, you may still get some charging around there. You know, if you crank your microprobe current up, you can get charging even on a coated sample. We will talk more about this and actually practice this with carbon coating on geologic samples later. That's the next slide. Okay, so there is something of a way around this. It's also not perfect, but it is available on our SEM. It's called variable pressure or environmental mode. Samples in an SEM that are either not stable perfectly under vacuum, or that it is difficult to make them conductive. It is still possible to get an image of them. Take example, if I want to image a red blood cell, you can find SEM images of red blood cells out there and take it. Red blood cells are not going to be stable under a vacuum, and I can't make them conductive. Well, what I can do is add a little bit of gas, because instead of the sample itself carrying away the charge, if I have a little bit of gas in the area that was otherwise under vacuum, so at the specimen stage, that gas can help remove charge, and it will help maintain materials that might not be stable under a full vacuum. So if my red blood cell is going to boil under total vacuum, and I let a little bit of gas in there, it can allow the thing to survive better. Now, the SEM has to be designed to do this, because my column has to be at a higher vacuum than my sample here, and there has to be a divider so that I can raise the gas pressure here, have a little bit of gas leak through the electron hole, but not so much that it overwhelms it. So our SEM does this, many of them do. It's called variable pressure or environmental mode. Another thing that raises the cost, okay? It does have some limitations. Increasing the pressure will block the beam somewhat. If you imagine driving through fog, this is like shooting an electron beam through a cloud. You absorb and scatter some of the light. That means you're not going to get the best pixel size. You might not be able to get that 10 nanometer beam in this case. So if you're trying to focus on the highest resolution thing possible, you may not get it if you need to go to variable pressure mode. It is also the case that if you have gas in your sample chamber, you will often almost completely block your secondary electron signal. That it will not be easy to measure at all because the electrons are just too low energy, they get absorbed. Backscattered electron imaging can substitute for that somewhat. It's not perfect, but you can often get a beam from that. If you really spend money on your SEM, if you got $5 million to play with and you need to measure cells, okay, you can design a system that takes the ionization from backscattered image electrons going through the atmosphere and detects that ionization to turn it into an image. You can build and buy systems like that. This is going to be well beyond this course, but they have that effect. There will also be an effect on any X-rays that are emitted from the sample, which happens to be 2 more slides away. We have a slide in here about managing contamination. RSEM does not have this. We had a question earlier about about the column damage and so on, about contamination. What happens if you stick something cold in there? You stick something that, if you are constantly trying to image things that have a lot of oil in them, things that have biological materials, that's going to contaminate your SEM. But if you give that contamination a place to go, a lot of it will get absorbed. Some SEMs can be built with a cold finger. In this case, liquid nitrogen being put in the back of this, cold finger marked right there. This is a spot where if material vaporizes, it is the spot where stuff will condense. And then you can remove that condensate material to minimize contamination. This is available on some SEMs. It is not on ours. This is one of those things that, one of those embellishments above and beyond what we can do. All right. We have 2 slides on X-rays and EDS analysis, and then this section is done. I have an advanced section in there that we can go through any other uses we want to. We have more than a half hour left. We'll see how much time we spend on this, okay? Electron bombardment sets off X-ray release from solid materials. There are 2 versions of this. Energy electrons slowing down as they enter materials just give off X-rays. Atoms interact with electrons in a specific way. We talked about secondary electrons where we knocked off an outer electron. What happens if I knock off an inner electron? If I knock off an inner electron from an atom, an outer electron will fall down to take its place. When that happens, it releases an X-ray. Dropping down an electron several energy levels releases an X-ray. That X-ray will have a specific energy, approximately unique for each atom, because the energy levels are different for each atom. So the amount of energy on each X-ray is quantized based on which atom it is. Serena will show you an initial version of this afternoon, or for group 1, and group 2 will do that in the morning, and then you'll get another chance to do this tomorrow afternoon. X-rays come off of material with certain energies as a function of the atoms that are present. If you measure the number of X-rays that come off with a certain energy, you can recognize, well, this material has iron, some phosphorus, some sulfur, some calcium. This is mostly iron oxide. This is an oxide material. A little bit of other stuff in it. Recognizing peaks can tell you what material is made of. Recognizing the intensities on a relative basis can actually identify a material. I can look at this and say, based on the peaks, this is an iron-dominated material here, whatever exactly this was that I found in Wikipedia. We will focus on how this works in more detail later, but this is what these spectra will look like on an EDS system, and we will go through how you can use some of this to identify materials later. All right. So,
are you done with this presentation?
Also in this presentation, if you want to come back to this later, I'm not planning on playing these, but there are a whole set of videos from this SEM's manufacturer on how to optimize images, how to do various things in this, how to optimize images part 2, electron beam settings, and so on for our SEM. So if, hypothetically speaking, tonight, you want to go back to review something that Serena said at 3:30 p.m. and see a video of it being done, the Nanoscience YouTube page is available to you. And you remember where I said that you have this all linked on that little flash drive? all these links are in there. So just enable the content. You can go play these on your computer later. Detector types. Okay. And I only loaded a few of these. I wasn't planning to play these because it's YouTube video, but if you need the reference later, that's what's there. Okay. How to enhance EDS. This is slower clicking from one slide to another than most. Okay, here we are. Oh, that's out of date. We kept having people drop in and out, so apparently I need to adjust this because we're back to 10 people as of, I think, yesterday. Okay. It is 11:30 right now. I have some other advanced SEM operations slides we can go through to take us up to noon. Okay, so there's many other SEM utilities we haven't talked about yet that we can spend some time on. The thing we need to get done more than anything else before we let you go for lunch is breaking into groups and having a plan for the afternoon and the mornings. So, Serena,